So the reactivity of the various type 1, type 2 carbonyl compounds varies depending on the identity of the group bonded to the carbonyl. For example, if you have acid chlorides and anhydrides, they are more electrophilic and thus more reactive than aldehydes and ketones. Whereas carboxylic acids, esters, and amides are less reactive than aldehydes and ketones. You can say less electrophilic. To make it simpler. However, aldehydes are more reactive than ketones, and we will study those. So if I have an aldehyde, such as acetaldehyde versus acetone, which is a ketone, then you know that if you put both of those in a vial and you add a nucleophile to them, then this will react in greater proportions than this one. So again, this is more reactive, less reactive. We will study this more in depth in the next chapter. So how can we explain this? So the relative reactivities depend on the relative stability of each acyl derivative. The least stable will be the most reactive. So we have two things going on here, and that's why it's not easy to resolve. We would have to look at two different factors that can be working against each other. And we've seen these before in the aromatics chapter. So the stability is dependent on the concentration of positive charge on the carbonyl carbon, which is dependent on a combination of inductive and resonance effect. So let's take a look. So if we have Z right here, that's an R group, we know we will have a delta positive, and we know we have a delta negative on oxygen. So we have, let's begin with the inductive effect. So this atom is an electronegative atom. Pulls electron density away from the carbonyl carbon. So basically what's happening here is that the electron density is moving toward Z at a time when the carbon needs as much electron density and negative charge to offset this positive delta positive, or if you have a resonance, the positive charge. So we say here that Z pulls electron density as we said, away from carbonyl carbon. And that basically results in making, which makes carbon more positive, which is less stable. So if you have, in this case, more positive on the carbon, it means it's more electrophilic. Okay, let's not play with words here. I don't want you to simply, okay, let's uh, just say these words electrophilic without understanding what it means. So think about it. If you have a positive charge on this, okay, and you're moving electrons away from it, then that positive only grows. So the more positive you hear, the more it will be enticing for an electron-rich and nucleophile to attack. That's what draws the nucleophiles is, again, there's a larger positive, more electrophilic carbon to attack. When it comes to the resonance effect, it may do the opposite. So if we redraw this, once again, we have a delta positive and we have a delta negative. So what is resonance? Moving this lone pair. So let's see what happens here. Where do you see the electrons going? You see the electrons going toward the carbon. So in this case, so the carbon becomes less positive because more delocalization of positive charge. So in this case, we say it adds electron density to carbonyl carbon, which makes it less positive. More stable. So now this is the opposite. If you have less delta positive on carbon, then it will be less electrophilic. So this might be, you might say, okay, so what's happening now? So notice again, the electron density going toward this carbon, offsetting this delta positive. Now, the idea here is, okay, so what do we go with? Do we go with resonance effects or do we go with the inductive effects? Well, we have to weigh them separately and we would have to determine the influence of each. And the greater the influence of one, then that's actually what's going to determine whether something is more electrophilic or not. This carbonyl carbon is more electrophilic or not. So to do that, so as we said here, the extent of resonance stabilization of Asol's derivative depends on how well the lone pair on Z can donate its electrons, and this correlates with basicity. So this is a lesson from Organic 1, very important. So all you need is this if you don't recall the base strength that we studied in Organic 1. So in Organic 1, we talked about how carbon, nitrogen, oxygen, fluorine, and then we have Cl, we have Br, and we have I. And we said that the base strength increases in the direction of the arrow, meaning this is the strongest base, and that means it's an unstable base, most unstable base in this series. And then this would be now the weakest base, most stable. So this is a whole topic that we studied in Organic 1, but it's, if you recall, it has to do with electronegativity and the size, the atomic size. So iodine is huge. So if you have the density, the electron density decreases over a larger area. And of course, fluorine would be more electronegative than carbon, so it can accommodate the charge better than carbon. So carbon doesn't have that much in terms of electronegativity or size to accommodate that charge, which makes it a very, very strong base. It cannot hold on to it for, let's say, for so long or just with enough strength. So let's look at the order of resonance stabilization. So I'm going to draw just one, choose one, and draw a resonance, a couple of resonance structures. So here we have them, all of these carboxylic acid derivatives, where imagine in this case O is Z, NH2, OET, etc. And then of course Cl. So if we just choose this one right here, or we can choose the oxygen here. So if we draw the resonance structure on this one, you would get just like what we did before. Okay, this one is not a nice looking bracket. There we go. So if you notice here, you have two equivalent resonance structures. So you have here resonance stabilized structures. So basically, it's not as electrophilic as you would expect it to be. However, if we look at the one at the end here, the chlorine, and if we put the lone pairs on chlorine, and again, draw another resonance structure. So we see a problem here. And that problem is the following. There's a positive on this chlorine atom. So first of all, the problem here is that chlorine can stabilize negative charges. So it's actually a very, very stable base in comparison to, let's say, something like oxygen. So in this case, what you're saying is that you're saying that you were able to donate electron density from the chlorine, which results in chlorine being, in a sense, electron deficient. So that is not acceptable. And there's also another reason. So we say here an acid chloride has the least resonance stabilization for two reasons. Chloride ion is the weakest base. It does not like to donate its electrons. And there's also a poor 2p, 3p overlap between the the resonance structure with a double bond between the carbon and the chlorine. Poor overlap, poor resonance stabilization. So let's look at the first one here. We had a carbon and we had an oxygen. So carbon and oxygen have the same, these are 2p orbitals, 2p, 2p overlap. They're in the same row, remember that, or in the same period. So it's a strong overlap in comparison. Whereas if you had the carbon and the chlorine, so I'm going to draw it right here, the carbon, so we can draw the small ones as we did. But then for the chlorine, since chlorine is, if you look at your periodic table, here's a carbon, here's the oxygen, the nitrogen, oxygen, fluorine, and then there's chlorine. So remember, this is 2p. And then for the chlorine, where you have sulfur, P, Si, this is 3p. So back to GenChem. These are the valence orbitals here would be in the, it would be in the 3 valence or valence shell. So third valence shell. So in this case, if you have Cl, it would be huge in comparison. So this is a 2p, 3p overlap. So this is a poor overlap.